Another phenomenon we'd like to describe with math and pictures or graphs are oscillations. Oscillations are anything that makes a motion that's periodic, or something that oscillates from one position, A, say, to another position, B, and then back to A and to B repeatedly. There are many examples from everyday life. You can think of bungee jumpers who have tied bungee cords to their legs and tied the other end to the bridge, hopefully, and then jumped off and they bounce back and forth, up and down. Or even a car in a ditch. So your car is stuck in a ditch and you try to push it out, but you don't quite manage to push it out, so it ends up rocking back and forth in the ditch. That's an oscillation. Or the pendulum in a grandfather clock, or there's lots of different examples. I'm sure you can think of some. For oscillating objects, if we want to describe it, we are looking for a particular or a unique position. And there is one where the position when the spring is relaxed. When the spring is relaxed, neither compressed or stretched, it exerts no force on the object that it's attached to. This is the equilibrium position. If the object is moved away from this position and released, it will oscillate about this position. Here's a picture describing this sort of this equilibrium position. We've attached a spring to the wall, so we have one end of the spring is attached to the wall, the other end is attached to a mass M1. The spring isn't compressed or stretched, so the spring is not exerting a force on the mass M1. So the dashed black line represents the equilibrium position. Now if we move it away from that position, say a distance A, we'll move it to what we call the release position. Because after we move it to that point, we're going to release it. Then the spring will pull it back toward the equilibrium position, and it'll accelerate all the way back to the release position and continue on past that point, then compressing the spring. It will travel to the other side, to the left-hand side of the dashed black line, a distance A also. So it'll oscillate from A to distance A to the left of the dashed black line to a distance A to the right of the black line. We're assuming that the floor has no friction, that there's no energy loss, so this oscillation will go on forever. How do we describe this motion? Well, just like in the previous examples, we have to pick an origin and also a time zero. So for time zero, we're going to use the time of release. This is a unique time because after you release it, the only force or significant force acting on the object is the spring force. So we're going to call that time equals 0. And we're going to choose the equilibrium position as the origin. There is another position that would be interesting in this problem called the release position, and we'll talk about that later. But for the moment, we're going to stick with the equilibrium position as the origin. In that case, that means that we are going to, if the origin is at the equilibrium position, we're going to have at time equals 0, the value of x or of our position is going to be A. It's then going to travel back through 0, the equilibrium position, and go to the other side, which will then be minus A. And we can describe this and then oscillate back and forth. We can describe this with the following equation. We have x, our position, as a function of time equal to A, the distance we've displaced it from the equilibrium position, times cosine of 2 pi times the number f called the frequency, which is a measure of how fast it's oscillating, times the time. We use cosine because it's an oscillatory function. It goes from 1 to minus 1. So when time equals 0, cosine of 0 is 1. So at that point, x at time equals 0 is A, as we see in the picture. Then if we wait enough time so that cosine becomes cosine of pi, so f times t is a half, then x of t will be minus A. So that will be the position when the mass is to the left, the farthest left it goes in the problem. If we go ahead and plot this, that's what we see. Here's our x of t is equal to A cosine of 2 pi f of t, and we see that the curve starts at A, goes down to minus A, back up to A, and so on. It keeps repeating over time. What if we had a different choice for the origin? What if we use the position of release as the origin, but keep the time of release at time is t equals 0. So we're still going to use t equals 0 to be the time of release, but we're also going to use that position of release as the origin. Well, the difference between the equilibrium position and that point of release is the value of a. And also we notice that x of t for this origin, so when t equals 0, x must be equal to 0 because we're using the point of release as the origin, and the time of release is the time equals 0. So when t equals 0, x must be equal to 0. So if we want to go ahead and change our equation for the position as a function of time, all we need to do is take a times cosine 2 pi f of t, f times t, and subtract off a to make it so that when t equals 0, we get 0. Or another way of thinking about this, we've moved our origin from the equilibrium position to the point of release, which has a value of a. So if we want to, that means that our equilibrium position now has a value of minus a. And that's where we're adding on to this x of t to make it work with the new origin. And if we plot this, we find that we have the position goes from 0 at time to minus 2a, which is the same physical position close to the wall, but now we call it minus 2a. And it's also passed through the origin, which is at minus a, and then it goes back to its original position at 0, back through the origin at minus a, back to the closest approach to the wall at minus 2a, and so on. Okay, I think we've hit this origin and equilibrium position well enough. There's one more point about oscillations that we need to talk about, and that's frequency. Here is our plot again, and we notice that it oscillates back and forth. Well, the number of oscillations per time has something to do with the frequency. You notice when you look at the plot that after a half a second, the plot repeats itself. So you have it goes up and down in half a second, and then it goes up, up. It starts out up and goes down and back up, and again in half a second. So if we look at it, we notice that there are 2 cycles, up, down, up, and then up, down, up, every second. This corresponds to a frequency of 2 Hertz, or 2 cycles per second. We can change this frequency, so here's a plot which goes from high to low to back to high in 1 second. Or in other words, this is an oscillation with a frequency of 1 Hertz, or 1 cycle per second. So we've talked about these oscillations. It turns out there are 3, and perhaps even 4, but we've been talking about 3 characteristic numbers that describe an oscillation. And these are the amplitude, how much you've displaced it from the equilibrium position, of course the equilibrium position, and what we just talked about, the frequency. So now it's your turn to go try and do a problem like this, trying to take a physical oscillation and turn it into an equation and then into a graph.